Hey, this is Professor Verkler, and today we are going to learn about power and energy in electric circuits. This is lecture 1-6 for ECE 1220 at the University of Utah. So our learning objectives today are to learn how to calculate power consumed by an electrical device, determine whether the device is consuming or supplying power, and be able to convert between energy and power. So if you remember from the first day, we had some cartoon drawings before we learned circuit schematics with a battery and a little incandescent light bulb. And so overall, we can think of circuits as transferring energy. So the battery in this case is supplying the power or the energy, and the light bulb is consuming power and energy. And the energy transferred per unit time is called power. And the power is transferred through current and voltage. So let's use dimensional analysis to find the relationship between power, current, and voltage. So power has units of watts, which is joules per second. Voltage has units of volts, and that's joules per coulomb. And current has units of amperes, which is coulombs per second. So I notice here that if I multiply voltage and current, units-wise, I see that's joules per coulomb and coulomb per second. So the coulombs cancel, leaving us with joules per second, which is watts. So therefore, power is equal to voltage times current. So usually that equation is written as P equals I V. Because I stands for current, and V stands for voltage, and P stands for power. Now we can combine Ohm's law and the power equation to get an equation specifically for power and resistors. But it's important to remember this equation will only work for resistors. And so resistors always consume power. They turn basically current and voltage into heat. And so the passive sign convention has us actually always drawing then the current arrow going into the positive labeled terminal for voltage. We'll talk more about that later. But yeah, this will always be true that for resistors, the direction of the positive current flow, that will be the more positive side of the resistor, and then the resistor basically loses voltage or loses energy in the direction of positive current flow. Okay, so let's combine these two equations. So power is equal to current times voltage. Voltage is equal to current times resistance in a resistor. So I can just plug this in for voltage to get P is equal to I times IR, which is I squared R. So if I know the current through a resistor and its resistance, I can calculate the power dissipated in the resistor. Now I could also plug in Ohm's law for I. So in that case, I is equal to V over R. If I go plug that in over here, I get P is equal to V over R times V, which is equal to V squared over R. So both of these equations are valid, and you just use the one that's appropriate in your situation when you're solving. So perhaps you only know voltage and resistance. And in that case, you can use V squared over R. Or if you know current and resistance, then you can use the other form, I squared times R. Remember, this is only for resistors. Okay. So to kind of summarize, power is a measure of energy per unit time, and its units are watts or joules per second. And the equation for power is current times voltage. And then energy is the sum of power over a period of time. And so we can use joules if we want, the SI units. Oftentimes in the US, you'll see things like kilowatt hours. And so this is the conversion factor. And the reason for that is joules is watts times seconds, whereas watt hours is hours. So to convert between seconds and hours, right, there's 60 seconds in a minute, and then 60 minutes in an hour. So that means 60 times 60 is 6 times 6 is 36, and then both those zeros are along for the ride. So that means there's 3,600 seconds in 1 hour. So that's why that's the conversion factor. Oh, can't see because of my head again. 3,600 seconds is 1 hour. Okay, and then the final thing to note is that for constant power, energy is power times time. We don't always have constant power. And by the way, power is like an instantaneous thing. It can change in time, right? See, this power is going up, up, up here, and then down, down, down. So power is just the instantaneous measure of current times voltage in the circuit at any moment in time. And so in this case, where power was changing and wasn't constant, we can't just multiply power times time. In that case, it would be an integral. And for those of you who don't know integrals, that's fine. You'll learn them in calculus coming up. And so an integral just means that it's the area here under the curve. And you could actually use geometry in this case, right? This is 2 triangles here. So you could calculate using geometry the area of each of these triangles to get the energy. Okay, I'm going to pause here and start a new video for the next section.